Well, hey there, you guys. It is time to go over this particular lovely AP question from 1987, the year I graduated high school. So this is from a very long time ago, without a doubt. Without a doubt. All right, let's see if I can't make this a little larger. There we go. All righty. So I'm sure you've hopefully taken a little bit of time and looked at this question and, gave it your best shot before you turned on this video. Otherwise, I'm going to say, hey, stop the video. Give yourself a chance and take a look at this question. All right? So I'm going to wait. Make sure you pause and you come back. All right, so assuming you've come back, let's take a look at what we're doing here. So this particular question has some interesting parts in the stem of the question itself. If you haven't noticed, let's take a peek. So you've got this situation here where you're going, this is our before collision over here, where we're dealing with this little blob coming at the bar. And then it hits it and smacks it. And of course, the blob then goes this way over here. And okay, this is going to bother me. I should really calibrate this, but we don't want to do that on tape. Let me see. I think I might pause and come back just because I know this will make me a little bit crazy. So let's bear with me here, and I'm going to pause for a second, and then I will come back and redo. All right, so we're back. Now let's try this again, shall we? All right. Oh, lots of little beeps in there. I'm just trying to make this go full circle. All right, there we go. All right, so as we take a look, the before collision is on the left. This little blob is heading in, hitting this bar. And so this one is coming in this way, and it hits the bar. Oh, that's much better. There we go. And then, so there's before the collision. After the collision, the bar has gone up, and after the collision, this guy is headed off in this direction a little bit. So a little bit different. The other thing, if you didn't notice, as you read it, let's see, linear momentum is not conserved in this collision. Really? Okay, but kinetic energy is conserved? Okay, now first of all, can that really be true? No, not really. But what the makers of this question are trying to do is they want everybody to answer it a certain way. And apparently if you answer it using conservation of linear momentum, you get a different answer, and they don't want that. So they're giving you something a little goofy here that can't really happen. And so that way you will work with conservation of energy versus conservation of momentum, or linear momentum. That doesn't mean that rotational momentum isn't conserved. Okay, so the other reason I know this question is from the 80s is they actually give you values. They give you numbers. It's kind of a different take on things, right? All right, so as we get ready to go here, a few things I just want to point out as we get started. When it comes to an extended body like this, lifting, and this will actually come up in part A, where you're doing the change in potential energy. What you have to consider, if we consider all of the mass to be through the center of the bar, if it's a uniform bar, you have to realize that the height that it goes up when you go to do potential energy changes is only half of the length. It's not the entire length. So keep that in mind as we go, so that it doesn't throw you too much for a loop. And I'm going to shift so we can actually get started on some of this. I made this a little bit smaller so that I should hopefully have a little bit of room to write. Here's my rotational inertia. They give that to us in there. And I'm going to save the numbers to the end. All right, so, or I might even not put the numbers in and say, you guys figure it out from here. You should be able to do that. No trouble. Okay, so question A says, determine the angular velocity of the bar immediately after the collision. So what you have to figure is after the collision, let's isolate it. I don't honestly care about anything going on over here. What I know after the collision, I don't care what's happening over here. I want to know this bar has some velocity at this point, and it has no velocity at this point because all of my velocity has turned into energy. And in fact, I just put the wrong velocity down. When you know it. It's not moving in a straight line, and I'm sure somebody out there is going, come on, Grady, get 2 days off for cold, and your brain turns to mush, and that's quite possible. All right, so we have an angular velocity because the ball's going to, or the rod is going to rotate up. It's not going to have one at the end. So when I get ready to do this conservation of energy for part A, so the collision has already happened. This is going to then, so I'm going to have rotational kinetic energy equal to gravitation. When I put my formulas in there for rotation, right, and then I'm going to, of course, put in my 1/3 ml squared omega squared equals GH. Before we actually do any more, I should mention, you should definitely mention that energy is conserved as an opening statement, which I just kind of forgot about there for a minute. Sometimes so do you guys. All right, so when we get this taken care of, let's consider what's going to happen here. My masses are going to cancel with no trouble, right? And my height, well, let's see, right here we've got 1/6 L squared omega squared. And over here, we're going to put in the height based off the length of the bar. And this is where I'm going to put L on 2. Because again, going back to my previous slide, it's the center of mass that is moving up. That's where we consider all of the force to be located, all the mass to be located. So we're going to say, how far does that go up? And that's only half the length. So from here, as you can well imagine, this is going to simplify even further down. And when you do the math, which I am going to suggest you do, because you've got all that stuff and you guys are math whizzes, you should get 5 radians per second as your answer. All right, that is going to be your omega final. All right. Part B, determine the speed of the 1 kilogram object immediately after the collision. Okay, well, if we want to consider that object, well, now we are going to have to go back and take a look. We are going to have to go back and take a look at, you know, what are we considering here? So if we got to think about this little guy, then what we're going to have to realize is, all right, we had some velocity before the collision, and then after the collision, we had the velocity. This is a linear velocity. And then, of course, we have the rotational velocity of the bar. So again, if we're not going to consider linear momentum being conserved, which is goofy, but whatever, people, let's consider, again, energy being conserved. Energy is going to be conserved. And what do we have? Well, at first we have the kinetic energy of the ball before the collision. We'll use that very high-tech notation right there. And then we're going to have kinetic energy of the ball after the collision, and then kinetic energy of the rod. This is just after the collision. So I'm not thinking about when the rod goes up to its max height. Okay, the snapshot I'm taking is right after the collision, just as that bar begins to move. So if you do that, 1/2 mv squared, this is my initial velocity, 1/2 mv squared, my final velocity, and 1/2 inertia omega squared. And again, this is the just after the collision. Well, long story short, again, we have pretty much all the values here. So do the math yourself. You should get a velocity of 8 meters per second. Alrighty, part C. Now part C is our first example of that weird little thing I was telling you about in terms of the, you know, something that is moving in a straight line, having an angular momentum, which sounds so strange. It just sounds so strange. But all things considered, if we're going to have an angular momentum of the bar after the collision, you have to have some sort of angular momentum to begin with, because linear momentum does not convert to angular momentum. That is the biggest mistake that we tend to make. All right, so part C. Excuse me, I need to cough a second. Hopefully I got that microphone out of the way so it wasn't too noisy. All right, so determine the magnitude of angular momentum of the object about the pivot just before the collision. Okay, so we're talking about that little blob. All right, so since it's a little blob, you're going to use this traditional formula for angular momentum, MVR. We already know its mass, right? We know the mass. We know the initial velocity because it's told to you in the question it's 10 meters per second. The radius, it is going to be acting along the length of that bar. So it's going to, your radius is going to be 1.2. Right now, keep in mind when we want something to apply ultimately a torque, a force, rotational force in order to make it move, it has to be applied at a 90-degree angle to that bar, to that radius, and that's at 1.2. So when you do the math here, you should get 12. And here's our wonky little unit, kilograms meters squared per second. All right, last question. Determine angle theta. Now here we might go, oh man, what am I supposed to do? This is where we're going to use some conservation of angular momentum. Okay, so again, you didn't convert linear momentum of the blob to angular momentum at the end. We are going to be using that angular momentum that we just figured out in part C, and now we're going to have angular momentum at the end. And this really helps us because in order to have angular momentum, again, you have to be hitting, you have to have the radius and the force, or in this case, the velocity that will cause the force, at a 90-degree angle to each other. So, so that's applied along that radius at a 90-degree angle. So what are we going to do? We're going to say that, initial angular momentum equals final angular momentum. Our initial angular momentum is 12, right? We just calculated that for part C, although you could set it up with MVR. And I'm going to be lazy and leave out the units, but we all know Mrs. Grady's lazy, so that's no big surprise. Now what I'm going to do is draw your attention back to this page here, and let's take a look at this. Now I'm going to get rid of this little guy here too. So let's get all that out of there. All right, let's think about this. Right, so let's consider where the bar was to start with. It was here, right? So when you look at this velocity vector here, what you need to think is, all right, that's not at a 90-degree angle, but it certainly makes a triangle, doesn't it now? This piece makes a 90-degree angle. That's the piece I want. That is, according to, if this is my hypotenuse, this one's going to be my cosine piece. So this is V cosine of theta. And that is how I get the angle in there, because it's that piece of the component that's in the conservation of angular momentum. Again, why? Because you need a 90-degree angle here in order to apply the torque that causes the change in momentum. So let's go back here. First thing we're going to talk about is the little blob, right? The little blob itself. We're using MVR, but again, we're going to use, we know the mass is 1. The velocity is going to be, now remember, we already figured out the velocity of the ball after the collision. It's 8. So this is going to be 8 times the cosine of theta, because we want the cosine piece in order to apply that torque there, and this gives us a mechanism to find theta as well. And the distance of the bar, 1.2. All right, but that's not the only object that has angular momentum after the collision, right? Because we also know that the rod itself has that. So this is where, again, you can pull in the 1/3 ml squared, and then omega is our omega right after the collision, which we've already figured out here is this 5 radians per second. So I'll just put in the 5. You have the value of m, you have the value of L. So at this point, it's a matter of algebra, which we're all quite good at. So you do that, and then hopefully you come up with 60 degrees for your final angle. The reason I like to give this problem is because I want you to see an example where there is this weird little point mass coming out of nowhere and wreaking havoc, and you have to figure out what's going on with it. All right, because too many times what I see as a teacher is I see you guys trying to take your linear momentum and smack it into an angular momentum. And I don't want you to do that. That's never how it's done. All right, so you're always going to figure that even if it's moving in a straight line, it can be applied along a radius and have angular momentum, even if it doesn't look like it's doing any sort of circular stuff. All right, we don't create angular momentum out of nothing. So we always put it in context with some sort of radius. All right, hopefully you find that helpful. And my goal, of course, is to see you in school on Friday. Let's hope for no more crazy weather. All right, talk to you later.